All right, and I hope you don't mind that I also let us run long the last session and here, because that cut out of the amount of time that I have to moderate Q&A at the end. So, yeah, so that's good. All right, our last speaker for today is Mike Agostini from MathWorks. Please, take it away.
All right. So, real quick before I get started, Mark, I think you were saying earlier there's a bunch of research going on right now that's asking the question, when are machines going to take over the world?
Yeah.
I think when machines start writing those papers, when are machines going to take over the world? That's when we need to worry.
And the words make sense.
And the words make sense, yes. And what's your name again? Philip. When you were talking at the end about what the future could be, I was reminded of the moment in The Matrix.
Yep.
When Trinity goes up to the helicopter and she says something like, Tank, I need a pilot program for B-212 helicopter or something like that. And 30 seconds later she can fly it. So it's a good vision. All right. So my name's Mike Agostini. I'm an application engineering manager. I'm a senior application engineering manager at the MathWorks, but I promise I still have some technical ability. Super promise. I'm here to talk about artificial intelligence for engineers, scientists, and researchers. And this is actually an adaptation of a seminar or a keynote that we put together for a world tour this year. So everyone knows MathWorks, right, is synonymous with MATLAB and Simulink. Sometimes people just call us the MATLAB company. But we're tool builders. So what that means is that it's our job to make your lives easier, to make it easier for you to do the interesting work. You're the engineers, the scientists, and the researchers in this statement. And what we're trying to ask ourselves, we've got a lot of thought into this, is how ready is AI for us, all of us collectively, and are we ready for it? So put another way, is AI ready for us? Is it a useful tool for solving the types of problems that we encounter as engineers and scientists and researchers? And the flip side is it a tool that we have access to that we can use to solve our problems? Or do you have to be a computer scientist? I know there are computer scientists in the room. Or do you have to be a data scientist in order to access these tools? So I'm going to talk about that. So wouldn't it be nice if, right, I could just ask Alexa, my Spark speaker, to write talks like this for us. But as it's already been pointed out, I think even Bob pointed out this morning, there are broad tasks and there are narrow tasks. And artificial intelligence today is much better at the narrow tasks, like Alexa, play me some music. And at MathWorks, it's really an exciting time for artificial intelligence because it's such an exciting time in the market. We have a recent study from Gartner, the results are here. And basically, if you read this, 50% of the organizations and companies out there want to do something with artificial intelligence. They think it's important. But only 4% of the companies have figured it out already. And this is just as of March of this year. So there's a huge gap in the market between the perceived demand and the actual attainment that this technology promises. Gartner takes this very seriously, by the way. Some of you who follow Gartner might be aware of the Gartner hype cycle. They've got this nice little graph that shows the various buzzwords and whether they're on in the valley of disillusionment or the peak of the hype cycle, these sorts of notions. They took artificial intelligence off of the entire list because they think it's for real. So I think we all know like the big AI type applications, smart speakers, of course. We've got facial recognition, machine translation. I delivered this keynote in Spain actually a couple months ago, and I don't speak any Spanish, and I was using this actually as the guest speakers were delivering their presentations. They would have their slides up in Spanish, and I would be using the same technology to auto-translate it. It was really fascinating. And then, of course, automated driving, which is very popular these days. But I want to share with you some of the other examples that we encounter at MathWorks, other people that we've helped with our tools from a wide variety of industries, including food processing, tunneling, mining and manufacturing, smart homes, as well as robotic prosthetics. Cool. All right, so back to lexicon, right? So artificial intelligence, we like to think of it at MathWorks as the capability of a machine to imitate intelligent human behavior. Maybe you heard this earlier. And actually, we think it gets really interesting when it's not just match, but it's match or exceed. So we're seeing applications now where vision systems in automobiles, for example, are more accurate than human drivers at detecting pedestrians and other objects. More accurate. And the degree exceed can also talk about the degree to which we can process, the speed to which we can process. And almost always when we're talking about machine learning, certainly everything we heard about today, we're talking about some notion of training a machine to learn the behavior that's desired. To learn the behavior that's desired. If we think about traditional programming, it's always been about this big puzzle. How do we get things like this, our computers, to do what the heck we want? It's all about getting computers to do what we want. And in the beginning, it was about writing programs to transform our data into output. But machine learning today really is about swapping the output in the program and using data, and often lots and lots of data, and the appropriate labeled output to build, maybe not a program, let's call it a model. A model that represents this behavior we're trying to capture. And as was noted earlier, in the literature today, when people are talking about artificial intelligence, they're almost always talking about machine learning. So in this talk, I'm going to be using machine learning and artificial intelligence interchangeably, but as was noted earlier, properly machine learning is a subset of artificial intelligence, but for simplicity. Okay, so we got data, we got output, and we got model. So a natural question is this all we need, or do we need anything else, right? MathWorks is tool provider, so we're trying to think in the context of the whole workflow. And I'll give you an example in the case of an automated driving system. So if you were designing an automated driving system, what else would you need besides data, output, and model? Well, you would need some way to access that data. For example, you would need to be able to connect to the sensors that you have deployed on your vehicles and retrieve that data in real time or pseudo real time. So that could be video systems, cameras, that could be LiDAR systems, which are measuring distances or range, that could be proximity sensors, a host of other things. We then need to be able to analyze that data and figure out the insights or the meaningful bits from it that we actually need in order to perform our analysis. And that could be reconciling two different data sets. For example, if you have an image system that's telling you there's a car in a car, and you have a LiDAR system which is telling you there's a car in a car, how do you know they're pointing to the same car? And then finally, we need to develop that uniqueness that is our intellectual property, or it's the fundamental question of our research. And then ultimately, we need to deploy these systems where we're going to use them. So in this case, if we were developing a system for a car, we'd ultimately need to be able to place it on the car itself. So in short, in addition to data output model, you need everything else. You need a whole system, a whole ecosystem. In that ecosystem, the data and the output and the model, or let's just call it the AI model, is just one more component. It's just one more tool in the develop category amongst a host of other tools we've already been using. So we're going to continue doing algorithm development in the future. We're going to continue doing modeling and simulation in the future. AI is not going to replace existing techniques. They're going to help us solve new types of problems that were unsolvable before. And then we can explore out the rest of these, sensors, files, databases, data exploration, analyzing, pre-processing, and ultimately deploying. Whether you're deploying to embedded devices like the car, or your desktop, or perhaps to the cloud, or other enterprise-like systems. And anyone here use Caffe or TensorFlow? Caffe or TensorFlow? I got some nods, okay. Caffe and TensorFlow are really good at building these AI models. So they're really good at a component of the overall workflow. And MathWorks Tools integrates with them. And you can build these AI models with MathWorks Tools as well. All right, so if that's our definition of AI, the next question is, do we even need this? Or what types of problems is it really good at solving? So if you consider this robot, for example, it's performing a pick and place operation, right? So the problem's well constrained. We've got sensors, the kinematics of the robot are well understood, the dynamics of the robot are well understood. In short, this is a problem we've been able to solve for 30 years, maybe more. So it's a well understood problem that does not require artificial intelligence. But what about the maintenance of this robot? How do you know when to replace parts or to service it? Do you just wait for the appropriate amount of time, or do you trust the person on the field who's listening to the motor grinding or observing the oil leaking out of the machine? And consider the scale of that question when you consider not just a single robot, but a whole fleet of robots. I think it was Ken earlier this morning that was talking about the body assembly plant at BMW that's not far from here. And this is a body assembly plant as well. I don't know if this is at BMW, but you can see there's hundreds of different robots all putting this body together. Each robot is unique. It's got slightly different tolerances, it's got different parts, there's variability in each of them. So the maintenance of these systems becomes a bigger problem. Even if these robots were exactly identical, down to the last micron, they're all performing different motions. They have different loads on their end effectors, and they're picking up different parts and moving them through different trajectories. So we'd expect them to all wear differently regardless. So this maintenance problem is a great application for artificial intelligence because AI is really good at the types of problems that require human-like perception or human-like judgment. All right, so those are the types of problems that we think it's really good at. So the next question is, can you folks use it? Now, obviously, a lot of you folks are already using it, so the answer is yes. But some of you haven't used it before. And there's a few questions that might go through in your mind, like, what if I've never used machine learning before? Well, I want to share with you one example from a researcher. This is at the Tech University of Munich. And what she was trying to figure out is whether or not snack food is crispy or if it's stale. Apparently this is a big problem in the industry because you have your food product that goes stale and you want to be able to, you don't want to sell that to your consumer because then they end up being unhappy. And it's not an easy problem. It's been approached in the literature from multiple different angles, including signal processing type applications. And she wanted to figure out if she could use machine learning to do this. Now, if you've never used machine learning before, one of the key components is you have to figure out what criteria you're going to use to sort into different categories: crispy, soggy, or something in between. And this is where we as domain experts bring a lot of expertise. We know our systems, we know our problems very well. And for her, when she thought about this problem, to her it came down to two factors: crushing force, the amount of energy it takes when you bite into that, and then the sound it produces at the same time in your head. And she thought if she could just identify those two features, maybe that would be enough to figure out if it's soggy or not. And that's the fundamentals of machine learning. You take some data, you extract your relevant features, whatever those might be, and then you use those to classify. Classifying is the act of putting it into different buckets, whether it's crispy, soggy, or something in between. Now, she knew her problem, but she didn't know anything about machine learning. And that's where, if you have good tools, this can become helpful. So this is one of the applications we have in MATLAB, which allows you to train models. And what this is doing is it allows you to select the data, arbitrarily pick which data you want, and then it will try lots of different potential models. Actually, the act of figuring out what model you need to use in machine learning is difficult enough that even the experts have to try a trial trial and error approach. So in this case, it tried multiple models. She selected the best one, and then she can look at how well the results do. So this is called a confusion matrix, but it's basically just telling you how often the machine is giving you the same results that human gave. How closely match the data set. Now that doesn't mean the human was right. This is just telling you how often the human and the machine gave the same results. So, okay. Are we ready for AI even if we've never used machine learning? Yes, absolutely. No experience required. Just bring your domain expertise and then use the right tools to help you over those hurdles so you can adopt these new techniques using tools that help do the heavy lifting for you. All right. Now, that required her to understand what criteria was important, the crispiness criteria, which was the crushing force and the sound that it produced at the same time. But often we don't know what the criteria are that we need. In fact, that's one of the big problems with computer vision problems historically, is it's hard to know what you're looking for. And that's where deep learning has come in. So if you consider the machine learning workflow, if that's data, feature extraction, and then some sort of classification effort, deep learning essentially just combines those two center steps, feature extraction and classification, into a single deep neural network, a single tool which will both look for relevant features, sometimes features that are not obvious to humans, often features that are not obvious to humans, and do the classification as well. So I got an example of this one. Oh, and let me say, compared to machine learning, deep learning takes a lot more data. A lot more data. You can see the little extra data icons, but it can be an order of magnitude, 2 orders of magnitude more. I mean, it's a tremendous amount of data you need for deep learning. So I want to show an example from the mining industry. So this is the Ted Williams Tunnel. It's in Boston. I'm from Boston. But this is relevant for any tunnel. So most tunnels today are manufactured with a process called the New Austrian Tunneling Method. Do I have any geologists in the room? So you're nodding. No one? Okay. So I could be totally making this up and you guys would be totally that's good. No fact checkers. Okay, so the New Austrian Tunneling Method is really complicated. So it used to be you would bore a tunnel through rock, and as you go, you supported it the same throughout. The revolutionary component of the New Austrian Tunneling Method is you look at the rock as you go, and when it's strong, you keep going, and when it's weak, you put up your supports. Revolutionary, right? Doesn't sound revolutionary now, but it was a big deal when it came out, and it saved a lot of money.
So they decide whether it's strong or weak.
Yeah, how do you decide whether it's strong or weak? So you have to have geologists that can look at the rock, this rock. No, that's a good question. And you have to evaluate on different metrics. There's actually 7 different metrics that they use. I'm not going to talk about all of them. I'm just going to explain 6 in extraordinary detail. They evaluate on different metrics. It can take hours to analyze, and there's a critical shortage of geologists. As we've already established, there's none in this room. I'm certainly not one. And their question was, can we train a deep network to kind of do this for us? Can we help augment the process without geologists? Can we suck that knowledge out of the geologist's brain and put it into some sort of model? All right. So the first problem that they had, so this is what they did, and they did do it successfully, but they had to overcome a couple problems. The first problem they had was they had 70 images, 70. That is not a lot of images. I mean, for deep learning, you need thousands of images at least, maybe tens of thousands. So what they did was they broke each image up into 10 to 15 other images. And they ended up getting, I think, between 1,000 and 1,500 images just by breaking them up. So that helped augment their data set. So once they had their augmented data set, they then sorted it based on, they had the geologists evaluate the images based on their criteria. Here's 3 of them, weather alteration, fracture spacing, etc. But there's others. Once they had those labeled, they then had to train a network. So does anyone know what you do if you need to train a network and you don't have enough data for it?
You cheat.
What's that? Transfer learning. Would you like a Rubik's Cube? I have a Rubik's Cube for you in the back for answering that question. Yes, you would like one. So they use transfer learning. So if you're unfamiliar with transfer learning, essentially what that does is it takes another network that has been trained with tens, if not hundreds of thousands of images to detect things like ice cream. And it retrains them to solve not an arbitrary problem, but your specific problem. Whatever you're trying to solve, or whatever you're trying to solve, or whatever you're trying to solve, you can use transfer learning to retrain a network to give you better results. And that's exactly what they did. So in the combination of both creatively splitting up the images and using transfer learning, they were able to come up with a technique that identified the rock correctly, and then they were able to deploy it to a web application so that the technicians in the field could use their iPads to take a picture, and it would tell them whether or not to put the supports up or not.
Is the transfer learning from an arbitrary set or a related set?
I believe they used, I'm not sure, actually. I don't know which
You know,
one
if they
they used.
inspected a whole bunch of rocks, that's sort of related. If they were actually doing ice cream and geese, that's like completely,
They might have used AlexNet, actually, but I don't know which one they used.
wow.
Yeah, so I can tell you which tunnel that they built, so you can stay away from it if you're nervous. They did.
Look at the image.
I don't know if, so I don't know a ton about the story, so you could ask me a lot of questions about what they did next, and I won't be able to answer them. And I do not know which tunnel that they built, so we're all flying blind here together. But to answer the basic question of whether or not we can use AI to identify, to help us even when we don't know those features, the answer is yes. So we have deep learning, which replaces a machine learning workflow, and it combines those 2 stages together, both the feature extraction as well as the classification. Now, so I have learned that Clemson has a site license for all students. So all students have access to all MathWorks products. And we're working on getting it for faculty and staff as well. But I've also learned that 84% of you guys and gals have already downloaded it and have it. So most of you have it. So all of you right now with 5 lines of MATLAB code, literally just these 5 lines, once you download, you have to download AlexNet too, which you can do through the App Store. But you can be running you can run a trained deep learning network from MATLAB, just like you see here in the image, to identify ice cream and cupcakes and hot dogs and other useful things as well in the privacy of your own dorm room. It's pretty cool.
Now, the modeling portion then is one has to manually, for each image, classify it using some criteria.
So in this case, AlexNet is a pre-trained network, and that work has already been done. But yeah, at some point, AlexNet was trained with a bunch of different images simultaneously. So when AlexNet was trained back in like 2012 or something, there were cupcakes and hot dogs and hamburger images all mixed in together. It was continuously trained with that as one big set.
But it wasn't trained with rock types.
No, it was not trained with rock types. But the way for deep learning, the way that the networks work, you have an input layer which takes the pixels, the raw pixels from the images, and then it does a number of layers that basically take a subset of those that are in a region and reduce it. And it's looking for features like lines and triangles and colors. So the first 2 lines of any image processing network, multiple layers, is is basically very similar to the same. It's not unlike, do you have any kids? So it's not unlike when you have a young child and you're teaching them their colors. And you can point to, this and they'll say black, and you'll point to, this and you'll say it's black, and this black, and they're all slightly different blacks. It's because, or triangles, like here's a triangle, and there's a triangle, and all these sorts of things. You're essentially helping them train all the layers of their convolutional neural network right there. And then they'll be able to use those things later to recognize stop signs, because you put an octagon and red together, and then it fires all the right neurons. So it's really fascinating, I think. It's only the last two layers that actually care about whether or not it's a cupcake or not.
Right, so but in that case, somebody has to manually specify this image.
That is a great question, and leads to winning a Rubik's Cube as well, if you wish, because that leads into the right thing, because you have to have that labeled data. And so we talked about transfer learning, and getting that labeled data is not easy. In fact, that's one of the biggest challenges today in this whole industry, is getting the data in sufficient quantities labeled to know what's a hot dog and what's a hamburger. And it gets even more complicated when you're dealing with other things like the rock types, and you need domain experts. So some of these networks are really good at training cats, for example, but everyone in the world can tell you if it's a cat or not. The problem's going to be in the future with these networks, when we have to solve complex problems that require someone with a PhD or an MD to tell you what the solutions are, because you're going to have lots of data, and it's going to be really expensive to have expensive people to label those. So that's an excellent point.
But is that related to, so often, getting the right question for the data you have? So for instance, you can have a bunch of data that says hamburger, hot dog, ice cream, whatever. But the real question I have is, what do I want to eat tonight?
Yes.
And how do you translate from between those two questions?
So what do you want to eat tonight?
Yeah. And I'll give you another example that's actually more to scientific data. So I'm a material scientist by trade. And material scientists over and over throughout, it takes 20 years is the paradigm for discovery of a new material to adoption. And you have material scientists going out there over and over back to the lab and saying, if I go from 3 significant digits to the tensile strength to the 4th significant digit, maybe now management will buy off on this and adopt my aluminum alloy. When the real question I want to know is, will the plane fly?
Right.
Right,
Or
or
how
will I
much
get
is it
fired as a manager for designing this into my plane?
Right. Or is it going to be, am I going to be able to manufacture that tolerances?
Yeah.
Or how much is it going to cost me to get that extra decimal?
And at the end of the day, because it's a manager and it's not an engineer, it really is a question of, am I going to get promoted or am I going to get fired in this
Right.
decision?
I have another slide, yeah. I have another deck where it talks about presenting in general. One of the things is, am I going to get fired or not?
Yeah. But how do you translate from this to that future state where it's, you have a data set, you have it labeled, you have all kinds of classification of this, but how do you translate that into decision-making within your organization if you're a company? That's a big picture question.
Yeah. Are you expecting an answer?
That's why it gets into the machine learning is AI, but AI is not machine learning. The machine learning is good for is-a, but not for, has-a kind of thing.
Yeah. So Mark, Bob, Mark.
Yeah.
That's a great point, because Bob, you had the 4 categories. One of them was decision making. One of them was prediction, I think. I can't remember what the 4 were, but I think you had 4 different things. But I think that's a good point in that this is answering the is a question, not what should I do question. But you can take this and present recommendations to right now for a human to kind of make the final decision. But the last example might be kind of exciting because it might be. Let's revisit the last example, because the last example is making decisions. So, all right. So I just want to wrap up this real quick in that what you see here is a LiDAR system displayed in MATLAB. And this is one example of like enormous amounts of data that we're being contended with these days as engineers and scientists. This is thousands of points per frame potentially thousands of frames over a few minutes, all of which simultaneously getting processed to identify which points are likely clustered together as a car, which are trees, there's a truck that just went by. And this is the sort of thing that AI is not just helping to build models, but is also being deployed to help recognize when clusters of things together represent a truck, for example. And here's another example I have that's part of the MathWorks products for automated driving. This is a tool that you can use to label different things like pedestrians, vehicles, etc. And then as the video plays forward, MATLAB will automatically label future frames, which will eliminate lots of manual labeling tasks. And here's another example of the final output, where you have both the labeled automated frames, this is all in a research design environment, simultaneously displayed to the side with the integration of a LiDAR system. So this is that sensor fusion is the phrase for it, where you have an image system and you have a radar system, and you're trying to reconcile them simultaneously to make better decisions. So, even if we don't have machine learning, we can still use these deep learning frameworks, but only if we have the data. Show me the data, show me the data. But what if we don't have the right data? I mean, what's one reason why we wouldn't have the right data?
Mislabeled kicks in, or just
Mislabeled is one, but what if we don't have any data
don't
at
have
all?
enough variability.
Variability.
I said edge cases, things that don't happen often.
Things that don't happen often. All right, you already have a Rubik's Cube anyway. Make it work. So, things that don't happen often, like this.
Oh my God.
So, one of the reasons why we don't have data is because we, as a society, think it's relatively expensive to run machines to failure, like this, just to get the data to train a model to tell us how things like this won't fail in the future. Also, if you consider like remote environments, like deep undersea or maybe spacecraft, those are not things that we can go up and like measure with probes very easily or very inexpensively. This actually did happen. I'm glad I wasn't there when it did. But we can use AI for predictive maintenance if we can get appropriate data for it. And we can if we have sophisticated models. Because we can't rely on data from the field. I think there's someone from GE here. The GE? Boom, right, I heard you say digital twin, right? This is right up your alley in GE, and this is where you guys are trying to go, right? Exactly. So if you have sophisticated models, like GE predicts and their notion of digital twins, or if you're using, for example, model-based design in Simulink, then you can have generic models, like this is a generic model of a wind turbine, and you can take real features from individual components in the field, like that variability of all those robots we were talking about, and then you can inject different criteria and run them to failure and observe the data that you get as a result of that. And if your models are of sufficient fidelity, then the data you collect is sufficient and adequate to feed, and, by the way, easy to label because it's all synthetic, to train these models that you can use then in the field. So even if we don't have the right data, we can generate difficult to obtain data using computer simulations or models, and we can use that data to train our AI systems. All right, so we've covered two of my examples. I've got two more I want to cover real quick. One is a smart home, and this was an interesting problem. So this is Denso. This was like one of their Toyota City Factory of the Future type things, home of the future type things. What they were trying to do is generate super low carbon homes. So they had solar panels, they had batteries, they had all sorts of sophisticated controllers inside to regulate temperatures. And they were also buying and selling energy off the grid. So they would buy when it was cheap and sell back when it was expensive, or they'd sell back some of the stuff that they generated through their solar panels if necessary. And they had that, you see that Toyota Prius, I think it is? They had a vehicle as well that had additional battery capacity. So they're also pushing power out to the car, and they were also selling power off of the car when they could. So the question they had, but all of that is solvable with existing technology except for one component of this problem that needs AI.
Fault protection.
Not fault protection, that's a good guess.
Prediction of when you want to use the EV.
Boom! Prediction of when you want to use the EV. You get a Rubik's Cube. When are you going to use this? A human could tell you, well, they're probably going to drive to work in the morning and probably going to come back at night, but only on Mondays through Friday, unless it's a holiday, then maybe they won't. Or actually on a holiday, they might be gone for vacation, as you know, we're coming up on a holiday this weekend, right? So for the whole system, they were able to design it all using conventional tools, a lot of the MathWorks products. For example, SimScape power systems to model the power systems in the home, model predictive control, and mixed image or linear programming to design their energy controller. You know, they could use different applications to generate stuff from the web, to get the electricity prices from the web. And only this one small component, the predicted vehicle usage component, did they need to deploy an artificial intelligence for, a machine learning application for. And for this particular one, and that was it. So you don't need to use AI for like these big, huge, complicated things. Sometimes if you have one small component of your problem you're trying to solve, you can just slide it in and continue moving forward. So their actual AI or machine learning algorithm was built from thousands of files. They use parallel computing. They use the classification learner app, which I showed earlier. And that was in conjunction with all the other tools they were using for the complete home. And ultimately, they can deploy it to the home itself. So they were able to significantly do this and reduce time. I think it was, I think they completed all this in 6 months. Yeah. And they attribute having access to the right tools as key to their success. Right. So the last example I want to give you, oh, yes.
Did they give you any ROI on the project?
They did not give us specifically ROI, or if they did, I don't have access.
Do you have an order, like an order of magnitude of how much the learn component paid into the system? You know, was it like another 0.5% or was it a?
Oh, yeah, no, I don't know that. That's a good question, but I have a feeling it's probably small. I mean,
Sure.
if it were 10%, I'd be surprised. Okay, last example, and I hope the audio works for this. So this guy, his name is Jason Barnes, and he's a drummer who actually lost his right hand. And I believe this is at Georgia Tech University. And what they were doing as a research study is trying to see if they could come up with a synthetic robotic prosthetic. So there's 2 sticks, you'll notice, a primary stick and then the autonomous stick. Now the primary stick is under Jason's direct control. And what I mean is there are sensors in that little, in the thing attached to his arm, which detects when he's trying to fire his muscles. So he can fire his muscles and he can get the stick to move. So you can see he's practicing or mimicking with his left hand and his right hand, so he can teach the other hand to remember how to do that. That's the primary stick. There's also an autonomous stick, and this is where we find out if the audio works. Pretty cool, huh? So the autonomous stick is actually driven by an AI and it's making decisions based on what it hears. So it's picking up the beat and it's making decisions when it can come in with more complex patterns to augment with what Jason's already doing with his primary stick and the other things he's doing. So the whole system is kind of structured like this. So Jason's the drummer and he's performing his music. And he's listening to the music and he's making changes, of course. But the prosthetic is also listening to the music and detecting from the EMG what Jason's trying to do with the primary stick. That's getting processed and getting run on a host computer that's got Simulink running on it with a PID controller. Simultaneously, There's a microphone that's listening to the total ensemble of the music, and that's where the AI comes in, and it's making independent decisions as to how to come in with more complex patterns with the autonomous stick. And this works not just with Jason practicing by himself, but this works in a complete ensemble with multiple musicians playing, in this case, jazz. I get choked up at this one usually. I just find it's, I am, sorry.
That's great, thank you.
I'm so proud that we, as engineers, scientists, researchers, we can help restore artistry to people like this. We are all doing it together. That's all I want to say on that. It's just, it's great. Quick time. Yeah, so I just wanted to wrap up real quick. I started this by saying, asking two questions. Are we ready for AI? And is AI a tool for us? And I hope I answered those questions. AI is a tool for us, but it's not designed to replace the tools we already have. It's an augmentation to add to the things that we already do. Algorithm development, modeling, simulation. It needs to fit in the whole ecosystem that we've become familiar with. It's particularly well suited for these complex tasks where there's a certain amount of variability, uncertainty, the need for human-like perception and human-like decision-making. And we are completely ready for AI because even if we've never used it, there are tools out there which help us bridge the gap. So we don't have to be deep computer scientists, although I know many of you are. And even if we can't identify features, our domain expertise is not enough, we can use deep learning methods to help solve problems that have never been solved before with other methods. And that requires a lot of data. Even if we don't have access to the right kind of data, then we have tools, simulation tools, that we can use to generate that synthetic data that we need. So, I'm from a tools company. So in short, I say that with the right tools, we're ready. And that's it. Thank you very much.
I know we've been asking questions the whole time, but we actually have a couple of students in the back of the tables, so we need to make sure they get to ask questions.
Okay, yeah.
So, in the back.
So you made a statement that AI has human-like judgment or human-like decision-making. I may agree with that statement for things like picking out, say, a cupcake or cupcake image. What are your thoughts about this statement when it comes to ethical issues and ethical judgments? Do you think AI is as good as a human, or will it ever get there?
So, I may have misspoke. I don't think AI is necessarily providing human-like judgment or perception. I was trying to say, when you need human-like judgment or perception, that's when it's a good case for one. But these models that we're building these days, they're not some mythical supermodel that is beyond the scope of what we're already capable of doing. They're just machine algorithms that are trained with data and us slapping its hand right or wrong when it's trying to make predictions. So there's no super ethical component to it. You could train it to do something, you could train it to answer ethical problems based on, you could train one to answer ethical problems if you have the right data, but I would certainly not trust it to make a correct decision in an ethical environment personally, because if the people who trained it fed it garbage, it's going to give you garbage out. And there's an implicit bias that we often don't consider, even when we're selecting the data to be trained. For example, if you wanted to make a prediction of all the attributes that make the best CEO in the world, for example, and you pulled all of the companies, this is not from me, this is from someone else whose name I can't forget, that I heard it from. But if you pulled all the companies and all the significant CEOs in the world, and you looked at their data, their age, the decisions they made, blah, 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 and you created the perfect model that would predict this person, whether you're going to hire or not, is going to be a good CEO in 30 years, you know what that person's not going to be?
Probably not a CEO.
It's not going to be a female. Because the historical data that we have is primarily male for all the CEOs. I mean, we do have female CEOs, don't get me wrong, but the data is so dominated. So a machine learning algorithm that is just taking the data you feed it, if there are implicit biases in there that we're not even thinking about, it's just going to replicate those. I think you were talking about the Microsoft example earlier, where Microsoft created an AI Twitter bot. Who was that? I can't remember. Someone was, but it's the same thing. It would, it turned into, in like 24 hours, it turned into a hate spewing, creature, because that was all that was getting fed to it. It was just responding to that. So, I mean, that's a long answer. The short answer is no, I don't think these things are good at ethical decisions, and we have to be very suspicious of the data we're feeding in them, and we have to be extra careful when we're looking at the output of them. I mean, in engineering applications, that's one thing, but when we're talking about human applications or making human decisions at mass scale, we have to be extremely careful with these things, because 9 times out of 10, if you build a model and the person who's using it doesn't understand the assumptions for which that model was built, it's very likely they'll misuse it or apply it in situations that were inappropriate. Does that answer your question?
Yes.
Okay.
Thank you.
So if we extend Bob's taxonomy this morning, I'm going to misstate it, but essentially that in some ways robotics is artificial intelligence for things that move around, right? Or what robots are. Can we wind up then saying, actually for artificial intelligence, we need to have some broader analogy to Asimov's rules for robots, right? In terms of, we're going to take this ethical question further and say we need to have some way of putting it in that context. And really this is for the academics in the room, for all the business people in the room. But thinking about these problems, this is the good kind of question to be asking in a
Yeah, I was just thinking about the 3 laws of robotics earlier today, actually.
So anyway, we have a question in the back.
Okay.
So, coming back to your question, right? Let me ask you, it's really a kind of what we call a subject that is really studied very deeply in company. Let me give you a simple answer to what you said. Imagine you have autonomous driving, and this is for a guy who's coding it, okay? The guy who's doing the coding, forget about deep learning, all that. Somebody has to make a decision, right? Imagine autonomous driving, a car is driving, and the situation is, there's an old lady on the left side, and you cannot stop. Okay, you have no option, you can drive. Left side is the old lady, and you cannot go forward. And there are 2 young kids or some young guy on the right side. Can you tell me the programmer to whom you will hit first?
The old lady.
You cannot. So whoever makes a decision is violating something, right? And the programmer cannot, right? So these are the things which is taking
At
credit.
the same time, this is the challenge with autonomous vehicles right now.
Yeah.
Because statistically, I mean, yes, you do have those individual instances, but and they are horrible instances. But statistically, if you wind up having more and more autonomy in a vehicle, which includes everything from the deployment of airbags to better cruise control, you're finding fewer deaths overall from highway driving. So I mean, this does get to a huge ethical dimension.
No, also who certifies this? right?
Well, my
At the
question
end-
earlier was who's gonna get fired for making the decision?
Exactly. So compliance is extremely vital.
And that's not an easy question to answer, even if it's a human driver, except for this gentleman.
So, variants of this trolley problem and the dilemma have been, so it's a comment, have been set up and presenting people with sort of a Hobson's choice of do you hit one or the other. But to go back to your comment about bias in the data, the third choice, which is really can the vehicle brake in time so that it hits neither, was conveniently left out in these hypothetical problems.
And could they identify the signal far enough in advance that you
Correct.
never get in that situation?
Correct. And so
That's my
these-
dad taught me when I was learning to drive. He's like, don't go too fast, son.
Exactly. So these are sort of set up from a philosophical / pseudo-legal setting where assume you cannot stop, and then you have a choice to make. And that the presumption at least is that, there are a greater variety of choices that you could.
So, to carry your extension, your example, to extend your example, if that AI can start the stopping process a half a second faster than a human could, or a second and a half faster than a distracted human could, then you're going to encounter far fewer instances where you have to make that decision.
I can't help follow. Following up on your question though, one of the reasons why that ethical problem becomes so hard is we don't have labeled data of which person chose which one of those people. And we kind of do, because you say, who would you pick? Just go to actuarial tables and the insurance people will tell you which ones to take out, right? They already did all the math, but they don't have the labeled data to train your set. So you just train something that you don't have confidence that it's modeling what you think it should have modeled.
So MIT has a website right now, I forget how to search for it, but they will present you with an infinite number of various dilemmas, and people are selecting who they run over.
But the other part is your hypothesis on that with the actuarial table is what you're trying to do is maximize global optimization as opposed to it's my family. Frankly,
Well-
those two kids aren't in my family, let's protect my grandma.
But to make it more visceral is do I sacrifice myself or take out
Yeah.
family? And everyone sort of says, well, of course I take myself out, but I'm not getting in a car that's going to value other people around me over me.
So that's actually so this is my personal view, but that's my personal view, is that the people who get into the car to accept for the technology's convenience, in my view, are accepting the risk.
Yeah.
And by the
Well,
way,
gee.
I'm not going to claim to be a data scientist, but I know when it comes to machines and projects for manufacturing intelligence and smart manufacturing, the project leaders will tell you that 70% of the effort is in the cleansing of the data to take away those anomalies so that the model that you create, that the machine will use is the best clean model. So, the getting the biased data out is one of the biggest things that they work on in that data science arena.
Well, we hear that too, that for the people who are doing machine learning with MATLAB, for example, they spend 9 out of every 10 hours doing the pre-processing of the data. The actual training is minuscule.
So do you want to store everything? Right now, if you're collecting data, you're not sure how you're going to use it?
My general perspective is if you're collecting it, you ought to store it, right? Because you never know what it's going to be used for in the future. And 5 years from now, you're going to wish you had collected something that you didn't. Some people had talked about edge automation, so there's augmenting of the data where there's computations that go onto the data, and then that piece is stored, but all the little micro pieces are not. So that's just my general perspective.
But there's a really highly efficient learning system that can store the data and does really well, which are people. So people, because they can't store all that information, figure out how to generalize the information on a general sense so that later they can process it. But you're right, if you can store, you can. But now, are you talking about turning your whole vehicle into a storage device so that you can store all the data? And even if you did, then you can't get to it,
But you also have, there's some data that you actually do want to forget.
Yes.
Like it's such an
Well, that's
outlier
the
that you
point,
don't.
right.
Yeah, and that's part of the cleansing is you've stored a bunch of data that you have no use for. but, you know, you may not be smart enough to know what that data is going to be at the beginning.
And what we're seeing, and what we recommend is a hybrid at the moment. So like these end sensors are gathering lots of data, and sometimes they make decisions right at the node, like right where the device is. And some subset of that you want to send to some sort of repository for doing post-processing on, or looking for general trends, like how to design the next vehicle. But like, if you're trying to figure out whether to brake to not hit someone, you want that data accessible and you're making a decision immediately. But you don't need the full, like, every single millisecond, how much slower you were going to be uploaded to a server at some point. You just might want the overall stopping time, for example. So there's different levels of data. There's like the really fine data at the end node, and then there's some data that you might want to put on a server somewhere, and then there's the data you actually pull down if you're doing analysis might be even a subset of that. So there's always some sort of sorting going on.
I would argue that depends upon what you're after. So as a tire company, I might be very, very interested in the millisecond by millisecond stopping capability of my product. Whereas for somebody trying to do driving algorithms, they're not.
Yeah, that's absolutely true. So different companies are going to make different decisions based on what they're trying to accomplish or what product they're actually producing.
And if you can model it accurately, then you store the model instead of data. So here is your classic example. In electricity, I talked about 10 petabytes per second, right? So what happened is this deposits energy in a given detector. You digitize that, and if you can model it into given 5, 6 points. So this is liquid argon. So when energy passes liquid argon, it gives a given shower. Lower energy will have a different shower. If you can model each of the parts of the shower into 5 points, instead of all sorts of distribution, then you're storing those 5 points and the function. So sometimes that produces huge set of data sets. So it's really important that if you can model it, store those ones. If you can simulate it, it's good. If not, you try to store as much as possible, which is needed. And the final point is that data is as good as the analytics on that. So if you store it and never use it, I'm not sure how useful it is. So it is as good as the analytics on that.
Got another question over here. We're, by the way, in the Q&A section of the agenda at this point, but that's okay.
I want to mention the methods deep learning tool uses of the existing deep learning general factor
TensorFlow and Caffe, or are you talking about like AlexNet and GooglyNet and those things?
So for your methods, you use your own.
Okay. So we have our own framework that we've developed, and we're building it out every release. And we also support Onyx, so you can import and export from Caffe or TensorFlow. So we've taken the position that you use whichever environment you want to use. If you want to use ours, great. If not, use whatever you want, and we will make sure you can suck those models in and use them in MATLAB. Yeah, I didn't have the slide in here, but we also support GPU, and we've been doing code generation for 20 years for other applications. We applied our code generation technology to the GPU stuff. We took it to the NVIDIA conference, I think last year, and we just completely crushed everyone's expectations. We were like an order of magnitude faster than anyone had ever been on GPUs before. Other people are starting trying to catch up now. I think they are, but it's you're talking about running an existing model. We're very fast at that. We'll math first, but there for you.
Mike, one question about ThinkSpeak.
Yep.
We are paying subscribers to ThinkSpeak and streaming data, real-time data for a couple of weeks. Have no idea what to do with it. What is the tool that the mobile office to run real-time data through the model?
Through the so I actually don't know a ton about ThinkSpeak, but ThinkSpeak is a MathWorks product. So I feel a little guilty about not knowing your answer, but I think that one we'll have to get someone else to answer that.
Well, so for everybody else, ThinkSpeak is a platform that allows you to stream the data in the cloud through a publish subscribe model. And once the data is is captured through the subscribe methodology, it can be acted on in real time using MATLAB code.
Yeah.
But, we don't know how to use it yet, so we're not doing anything. Other than making progress.
Do you know Debbie, the account rep for Clemson?
No, I do not. There's somebody else that deals with it.
Okay.
Michael, I think. Microsoft.
Okay, but if you get a hold of that person, we can get some
But
answer questions.
I would think that it needs, it probably has a very clear linkage, right? So
Oh,
that's-
certainly.
That's what you want to do, is link the real-time data to this model that you just created.
Yeah.
And make decisions based on it.
Bob, we'll let you get the last question of the day now.
You talked a lot about the machine learning aspect in MATLAB. Do you have stuff on the expert system side or any of the sort of the more classical AI decision support?
Do you have an example?
So something like inference engines or something that would do back propagation, like a Reedy engine or some, more of your rule-based kind of goes through and expert systems. Yeah, expert systems or.
So, I don't know. I think we do. So we have the neural network toolbox, which does the deep learning, but in addition, we have the statistics and machine learning toolbox. And a lot of those back propagation, various classification technologies are in there, classification or sorting algorithms, bag tree, those sorts of things are in there. I don't recognize the specific ones you're asking for or asking about. But that's where I would check is the statistics and machine learning toolbox, not the deep learning toolbox.
Great.
Cool. All right. Thanks, everyone. And I have some little wind-up tubes and maybe one or two more Rubik's cubes and some things you can stick on the back of your phone. And I'm not flying back with them, so just leave them on the table. Anyone who wants one can grab them.
Great. Thank you. And also, relative to MathWorks, I'm glad to actually say this because I've heard you all for years and years and years to be able to thank someone from MathWorks for years of sponsoring public radio, by the way. You guys have done that nationally for years and years, so thank you. All right, well, I want to thank everyone. I don't know if anyone's got any wrap-up comments that they want to have from the field as well. I've got a couple of things I want to point out. We've got an opportunity to take a sort of an informal tour over at the ICAR facility after this. I'd be happy to arrange that for people that may or may not have been over there. Also, we've got a survey. Rebecca, surveys on each table, or where are they? There's a link on the invite on your file. If you can wind up responding to the survey, that would be really helpful for us to understand and learn in the sense of this. I'm not sure we're going to put together, we're going to have a deep learning algorithm. Yeah, no survey, but we're going to promise we'll put some sort of deep learning algorithm to the responses to be able to. Yeah, that's what you're going to do.
We'll develop this all.
Okay. So, and we'll get that done. The last thing I'm going to wind up saying, we'll see if people are interested. How many people here, first of all, Clemson University has a football team, right?
Yes.
So there's apparently a game tomorrow, and so we actually have a couple of extra tickets. So anyone that might be interested in that, you're welcome to come up. I think we'll figure out how to do some sort of raffle if we have more than 3 people come up that would be interested in tickets. But we've got a couple of extra tickets if you're interested. Please see me after this. I guess I will volunteer to be the person to wind up getting either bombarded or standing there and saying, who wants to buy some tickets? Anyway, not buy, but have some tickets. And with that, I don't know, I will say, just wrapping up, I'm actually both optimistic, and I mean this really positively, confused about artificial intelligence. I was sharing with some of my colleagues yesterday that I've taken one and only computer science course in my life, and it was my freshman year in college in 1980. And I walked into the class and actually, I learned, like I said, some killer Fortran, but learned Lisp and Pascal on it. And for those of you who are computer scientists here, I had no idea who this guy's name was. JCR Licklider was the guy who was teaching it in his last class. And for those of you who may not know, he started the Information Technology Division at DARPA and essentially predicted the development of and put the framework together for the development of artificial intelligence and all of this. So I felt lucky to have had that one and only computer science course in my life. Back then, and this was just at the emergence of like the personal computer era, you knew that this mattered. You were at the age where to learn how to program, literally you were learning how to do things like assembly code. It's like shift left, shift right, put things in. You're doing all these little projects you're putting together to learn how to do these things. It was fun more than anything else, but you were learning. You also knew that something big was going to come out of that. And 15 years later, you suddenly had things like HTTP come out, the internet come out, it just took off. It shows my age on that. Artificial intelligence absolutely feels that way right now, and it feels actually more developed than that right now. And just encourage you all to keep working in this area and constantly do some great work in this area, engaging with industry, and let's go forward. So, all right, thank you all.